Okay, so for the last talk of this session, we have Josse van Dobben de Bruyn, who will talk about asymmetric graphs with quantum symmetry.
Thank you for the introduction, and thanks for the organizers for inviting me. Today I'll be talking about asymmetric graphs with quantum symmetry. So I'll show how to use ideas from quantum information theory to get a result in non-commutative geometry, where we construct classical graphs that have no symmetry at all, but there are somehow these hidden quantum symmetries. I think this is a very interesting topic that connects two of the three main themes of this workshop together. I'm sad to say there won't be much operator algebras, but okay. This is joint work, by the way, with David Robertson and Simon Schmidt. Okay, so the outline of the talk for today, I'm going to say a little bit about the background here. So quantum isomorphisms and automorphisms and where they come from. So there's going to be some motivation, and then in the last part, I'll explain how to use ideas from quantum information to construct these asymmetric graphs with quantum symmetry. Okay. A quantum permutation matrix, as we've seen in other talks before, it's this matrix U with entries in a C-star algebra, such that all the entries are self-adjoint projections, and the rows and columns sum up to 1. And the first part of my talk will be motivating a bit why is this a quantum permutation matrix. We can see that this is a generalization of classical permutation matrix. For a classical permutation matrix, you take the C-star algebra to be just the complex numbers, and then you have self-adjoint projections, so there must be zeros or ones, and because there's the rows and columns sum to 1, that means that there must be exactly 1, 1 in each row and each column. But okay, so this is a generalization. Why is it the right one? I'll say a bit about that. Here is some like generic example of a quantum permutation matrix. If you have two projections, P and Q, then you can, for instance, make a matrix like this with P, 1 minus P, 1 minus PP, and same for Q, and then the rows and columns sum up to 1, but in general, P and Q do not commute necessarily. Right. And now the definition of isomorphism, quantum isomorphism between graphs before I go to the motivation. So I'm going to assume here that a graph is a finite, undirected, and simple graph. And the adjacency matrix is just a 0, 1 matrix A, where the xith entry is 1 if there's an edge and 0 otherwise. So for graphs, we note that there's a classical isomorphism between x and y, if and only if there is a permutation matrix P such that the adjacency matrix of x is P times the adjacency matrix of y times P inverse, or equivalently P intertwines in this way the adjacency matrices of the two graphs. And based on this, the definition is, well, a quantum isomorphism between two graphs is a quantum permutation matrix that intertwines the adjacency matrices. Okay, so far for the definitions. Now, heading over to motivation. So there's two ways to motivate quantum isomorphisms and quantum automorphisms of graphs. One is from non-local games. Sorry, wrong button. And the other one is from quantum groups, and I'll say briefly a few things about both motivations. So, non-local games, we've seen this many times before in the workshop. We have a referee who asks questions to Alice and Bob from some fixed input sets IA and IB. And then Alice and Bob answer with their answers from the output sets. But Alice and Bob are not allowed to communicate during the game. And then the players are playing together and they win if the tuple of inputs and outputs satisfies some winning predicate. So a well-known example is the Merriman-Paris magic square game. This is an example of a non-local game where you have no perfect classical strategy, but there's a perfect quantum strategy. Here we have a grid of 9 variables, let's say binary variables, 0, 1. and we want to make an assignment to the variables such that the variables in each row sum to 0 modulo 2, the variables in each column sum to 1 modulo 2. Classically this is impossible, but then it turns out that there is a quantum strategy for this. Where, okay, so I guess here Alice, let's say Alice is asked one row in the game, so I need to formulate it as a game. Alice is asked one row and should answer with an assignment to the variables that occur in that row. Bob is asked one column and should answer with an assignment of the variables that occur in that column. And then this one variable where the row and column overlap, the answers of Alice and Bob should agree. That's the winning predicate. So here there is no perfect classical strategy because it's impossible to find an assignment of all the variables that satisfies all these equations. That's just because the total sum of the variables cannot be both 0 and 1 mod 2. But there's a perfect quantum strategy where you use these Pauli matrices. So you have these Pauli matrix sigma x and sigma z, and they satisfy these properties that they square to the identity and they anti-commute. And from that it's easy to check that this is an operator solution to the linear system, and from that, using some standard modifications, but they're not, I mean, some of these results maybe in general are not trivial, but there are some modifications that you can translate this into strategies for the game. Okay, so now we go to the isomorphism game. If we have two graphs x and y, then the isomorphism game is a non-local game that models an isomorphism between the graphs. I guess we've seen this before in the other talks. I see that on my slides I have a different version of the game where the input sets and the output sets are the disjoint union of the vertex sets. There's an equivalent version of the game where you are asked always a vertex in one graph and should always answer a vertex in the other graph. But here, Alice and Bob can be asked a vertex from either of the two graphs, and they should answer a vertex from the other graph, so that's the first condition. If Alice is asked a vertex from x, then she should answer a vertex from y, and vice versa, and likewise for Bob. And then relations should be preserved. So if Alice and Bob are asked the same vertex, they should answer the same vertex. If Alice answers with Bob's input vertex, then Bob must answer with Alice's input vertex, and so on. And then the theorem by Lupini, Marcinska, and Robertson is that this non-local game, the graph isomorphism game, encodes these definitions of quantum isomorphisms between graphs that we've seen before. So there's a perfect classical strategy if and only if the graphs are isomorphic, and a perfect quantum commuting strategy if and only if the graphs are quantum isomorphic, where the definition was, remember, with this quantum permutation matrix that intertwines the adjacency matrices. And so we denote quantum isomorphism between graphs as this isomorphism in the QC model. And then you can use techniques from non-local games to show that there exist graphs which are not classically isomorphic, but they are quantum isomorphic. You can take, for instance, this Mermin-Paris linear system, and from that construct some graph in some way that encodes this system. And here you get, you take one graph for the homogeneous system where all the equations are 0, and then one graph for the inhomogeneous system. And then it turns out that these graphs are not isomorphic, but they're quantum isomorphic. And this will be the basis for our construction later, will be a similar construction of this graph, and similar techniques will be used to get asymmetric graphs with quantum symmetry. So that's one motivation for why these quantum isomorphisms are the right definition. Let's look at the other one. So from quantum group point of view, So very brief background on quantum groups. Quantum groups are a generalization of groups, like non-commutative analog of groups. They were discovered from various different viewpoints. So as deformations of Lie groups and Lie algebras, as a superclass of groups that allows you to do Pontryagin duality for non-abelian locally compact groups, and as the quantum symmetry objects of spaces in non-commutative geometry. And I will focus mostly on the latter point of view. So we think of quantum groups here as the quantum symmetries of some graph. In general, in non-commutative geometry, you use this Galfand duality. So you say, you note first that by the commutative Galfand duality, you have that locally compact spaces roughly correspond to commutative C-star algebras. And then you define a non-commutative space to be just any non-commutative C-star algebra. But then actually the space doesn't exist, so it's sort of a formal dual object, really, of this C-star algebra. And then you can define various notions of structure on top of that. So for compact quantum groups, you say first, if we start with a compact group, then you can put some structure on this C-star algebra. And this is just the algebra of functions on the group. And there is some co-multiplication structure now on them. And then you say, okay, we define a compact quantum group as a non-commutative C-star algebra with a co-multiplication that satisfies certain axioms. And again, here the quantum group itself doesn't really exist. You only have the algebra of the group. Okay, so if we have a classical compact group, then you can recover the multiplication structure actually from this co-multiplication that's defined on the functions on the group. And this co-multiplication is just this map from C of G to C of G cross G that does this. And sort of inspired by this, Voronowicz defined a compact quantum group as a tuple consisting of a unital C-star algebra together with this co-multiplication map that satisfies certain properties. So there's this co-associativity and this cancellation property. I'm not going to say much more about quantum groups here, but maybe one thing is that if you have a compact quantum group and the C-star algebra is commutative, then actually you can show that it comes from a compact group in the sense that this proposition shows. So there is a compact group so that delta is exactly this co-multiplication. I'm going to give two examples now of compact quantum groups that come up in our construction of asymmetric graphs with quantum symmetry. The first is the dual of a discrete group. So if we have just a group with no topology, discrete group, then the group C-star algebra can be turned into a compact quantum group with, well, this co-multiplication. Actually, the co-multiplication will not be very important for this talk. So for us, we can just focus on the C-star algebra. It's going to be just a group algebra. And if the group we started with was abelian, then this is just the Pontryagin dual of the group, but viewed as a quantum group. And then the other example is this family of compact matrix quantum groups. Here we have a unital C-star algebra generated by a matrix Uij, such that the matrix Uij and its star, like its entry-wise star, they are invertible matrices. And this map that vaguely resembles matrix multiplication defines as unital star homomorphism. Then you can show that this thing is actually a compact quantum group. And this is the second class of examples that we're going to draw from. Now we get to the definition of the quantum automorphism group of a space in non-commutative geometry. This is the very general definition. The idea is you define what it means for some class of spaces, what it means to act on them by a compact quantum group. And then if there is a terminal object in the category of quantum groups acting on X, then we call that the quantum automorphism group of X. So the terminal object, that just means that whenever something acts on X, then there is a unique morphism from that compact quantum group to the quantum automorphism group. And by standard category theory arguments, it's trivially easy to see that this must be unique if it exists. You need to show that it exists. And then the first class of objects for which this was shown to exist was the quantum symmetric groups, which were defined and proved by Wang to be the quantum automorphism group of the finite point set 1 up to n. And you get that as a compact matrix quantum group, so we show that it's isomorphic to the compact matrix quantum group generated by Uij with the relations that the entries are self-adjoint projections and the rows and columns sum to 1. So in other words, this is the universal C-star algebra of a quantum permutation matrix. Okay, so based on this, Banneker defined the quantum automorphism group of a graph to be the compact matrix quantum group where we take the same relations as before, but we add this relation that now this quantum permutation matrix commutes with the adjacency matrix. So as a C-star algebra, this is going to be a quotient of the C-star algebra of the quantum symmetric group. As a quantum group, we say that this is a quantum subgroup. And I should point out that there is a different incompatible notion of the quantum automorphism group of a graph, where, so for Banneker's definition, the notion of an action of a quantum group on a graph, it's only permuting the vertices in a way that's compatible with the adjacency matrix, but Bichon adds this condition that there's also a quantum permutation happening on the edges. And classically that's automatic, but in the quantum case it's no longer automatic, so you get, in general it can be a different quantum automorphism group, but it's always a subgroup of the one defined by Banneker. And nowadays it's more common to study the larger one that Banneker introduced. And the point of all this is to say that these quantum permutation matrices come up naturally both in non-local games as the strategies for the isomorphism game, and in quantum groups as the elements of these universal symmetry objects in non-commutative geometry. That said, now we can get into the meat of the talk where we construct asymmetric graphs with quantum symmetry. So various authors have asked what's the maximum disparity between the automorphism group of a graph and the quantum automorphism group. So questions like this look like, for instance, is it possible to have an automorphism group that acts intransitively, but the quantum automorphism group acts transitively? Or is it possible to have a trivial automorphism group and a non-trivial quantum automorphism group? Or somehow a question that combines them, is it possible to have a trivial automorphism group and a transitive quantum automorphism group? So for the first question, the answer is yes, and this was answered by Lupini, Monchinska, and Robertson in 2020. Second question, answer is also yes, and that's the topic of today's talk. And the third question is still wide open. Goal for today will be to show how to construct these graphs that answer the second question. And now, on this slide, I'm going to give a high-level outline of the main idea of the construction. And if I want you to take anything away from this talk, it's going to be this slide. So we use ideas from quantum information theory to construct before they were used to construct graphs that are not isomorphic but they're quantum isomorphic. Now we want to do something similar, except somehow from the graph to itself. So there's no automorphisms, but there are quantum automorphisms. So for these, when you had two graphs that are not isomorphic but quantum isomorphic, the construction came from this Mermin-Paris magic square. So this follows from a more general class of non-local games, where you have a linear system that's inhomogeneous, a linear system over F2, and there are no classical solutions for the linear system, but there is an operator solution. So this is the operator solution from before. Now we're going to do something similar, but with a twist. So instead of taking an inhomogeneous linear system, we now need to take a homogeneous linear system, mx equals 0 over F2. And it's always going to have a trivial solution, but we want to find a linear system that has no non-trivial classical solutions, but there exist non-trivial operator solutions. And then from there we construct graphs in a similar way as before, and that will give us the asymmetric graphs with quantum symmetry. Okay, so here is a more detailed outline of the proof. We start with some linear system mx equals b over F2. From this we study the homogeneous solution group, and I will say in the next slides what all of this means. From there we construct a colored graph where the quantum automorphism group of the graph is isomorphic to the dual of this solution group. And finally we do something so that we can remove the colors and end up with an uncolored graph with the same property. Okay, so a colored graph. What's a colored graph? For me, a colored graph is just going to be a vertex colored graph. So we have a finite simple graph with a vertex coloring, and I don't require that this is a proper coloring. So adjacent vertices can have the same color. That's fine. And for these graphs, we define the quantum automorphism group as before, but we add this extra condition now, that if the vertices I and j have different colors, then we set uij equal to 0. And you can just think of this as saying colors need to be preserved. So you may not map I to j if they have different colors. So here are some examples of colored graphs with their quantum automorphism group. If all vertices have the same color, and we take, say, the complete graph, then the quantum automorphism group is just going to be the quantum symmetric group Sn+. A non-trivial graph for which we now know the quantum automorphism group, thanks to a result by Simon, is the Peterson graph, which actually the quantum automorphism group is just a classical automorphism group. Now here's an example of a colored graph with more than one color. So we have two red vertices and two blue vertices. Here the only classical automorphisms are the identity and the reflection about the y-axis, because the other ones, the other automorphisms of the square, don't preserve the colors. And you can show that this is also the only quantum automorphisms. And then finally, maybe to advertise a different paper that we've worked on, to classify quantum automorphism groups of trees, we also use these colors to give an algorithm to actually compute the quantum automorphism group of an arbitrary tree. But I'm not going to say more about that now. Okay, so now the next step is the solution group. So I'll define what a homogeneous solution group is of a linear system, and those who have studied linear system games will recognize this from non-local games. If we have a homogeneous linear system mx equals 0 in n variables over F2, then a group valued solution is a tuple h1 up to hn of elements of some group h, such that hi squared to 1, and for every equation in the linear system, the elements that occur with non-zero coefficient in that equation they must commute and multiply to 1. So we have a solution where for each equation the variables commute, but globally not everything necessarily has to commute. And the homogeneous solution group, as defined by Cleve, Liu, and Slofstra, is the finitely presented group with generators h1 up to hn subject to these relations. So it's the universal object that encodes all these group valued solutions. Right. Now I'll say a little bit about the construction. It's going to look similar to the construction from before for quantum isomorphic but not isomorphic graphs. So given some linear system mx equals b, we define x hat m comma b to be a bipartite graph. Well, I'm just going to give an example here so we don't have to bother with the notation. For every variable in the linear system, we make 2 vertices. One for the 0 assignment, one for the 1 assignment. And then that's going to be one part of the bipartite graph, is all these variable vertices. And then on the bottom part of the graph, we take these equation vertices, where for every equation, we make vertices for all valid assignments of the variables that occur in that equation. And variables that do not occur in that equation, we ignore them. So for instance, here we have this equation x1 plus x3 equals 0. So we put a vertex 0 question mark 0 and a vertex 1 question mark 1. That's all possible assignments of the variables that occur in that equation and that satisfy the equation, I should have said. Yeah. And here we got 4 instead of 2 for the other equation. And then finally, we make this into a colored graph by giving every variable and every equation all its own colors. And the edges are from every equation vertex to the corresponding variable vertices. So for instance, here we have 0, 1, 0. So we connect it to the 0 vertex of x1, connect it to the 1 vertex of x2, and we connect it to the 0 vertex of x3. This is a colored graph that somehow encodes the linear system, and it turns out that this is going to give us what we want. So what we proved here is that the quantum automorphism group of this graph is isomorphic to the dual of the solution group. So remember, the solution group is a classical group, but if you take its dual, then that's going to be a quantum group, unless the solution group was abelian, then the dual will be a classical group. But typically this is a quantum group. And then as a consequence of this, it follows that the classical automorphism group is going to be isomorphic to the dual of the abelianization of the solution group, but that's just isomorphic to the kernel of the linear system, actually. Yeah, I'm going to skip this. Okay. So now for every colored, sorry. So now the next step is we need to remove the colors of the graph while keeping the same quantum automorphism group. So for this we do the following decoloring procedure, or actually I'm not going to go into detail here, but we show that there is a decoloring procedure that turns every colored graph into an uncolored graph with the same quantum automorphism group. And an example of what that could look like for this particular graph from the previous slide is for every color you add one vertex that you connect to all vertices of that color. So here for the purple vertices, there's going to be one vertex connected to all 4. And then on those added vertices, you add paths of different lengths. And that forces them to not only classically, but also for the quantum automorphism group, they can be distinguished from each other. So you can recognize the colors from these gadgets. And this is a very common technique in graph theory, in computer science, to replace colors by gadgets. Okay, and then the final step, and that's sort of the interesting step, I think, is to choose the right linear system. So we have, for every linear system now we can write down a graph that's an uncolored graph where the quantum automorphism group is the dual of the solution group, and the classical automorphism group is the kernel of this matrix M. So to get asymmetric graphs with quantum symmetry, we want to find a linear system such that the kernel is 0. That means the automorphism group is going to be 0, and the solution group is non-trivial. Okay, that should be doable, maybe. But then the first approach you might want to try is try some small systems for which we know that the kernel is 0, and then compute the solution group. But the solution group is a finitely presented group. So now you're trying to solve a word problem, which in general can be undecidable. So it's very hard if you approach it this way to tell which systems are going to work. So we need a trick. We need to be more clever. And that's what we did. So again, the goal is to find a matrix where the kernel is 0 and the solution group is non-zero. And the idea is now we're going to start with a target group H. We have some group H that we want to write a system so that the solution group has a homomorphism to H. And for this, we take, it's sort of similar to this idea in group theory where you take a finite presentation of your group by just a multiplication table. So, but here we cannot do that, but we can take all the solution group relations in H. So for every element of order 2 in H, we make a variable xh. And then whenever 3 of these elements of order 2, they commute pairwise and they multiply to 1, then we make a linear equation like this. And this is just encoding all the relations that hold in H that you get in a solution group. So in particular, there is a group valued solution to the linear system. You should just set xh to H for all H. You have to translate here between the additive notation and the multiplicative notation in the group. So, but in the solution group, this equation is satisfied if and only if xh1, xh2, and xh3 commute pairwise and multiply to 1. So you see that this is a valid solution. So that means that whenever H is an element of order 2, there is some homomorphism from the solution group to the group H, namely the one that sets these like universal generators xh to H. And the image of this homomorphism is non-trivial, so that means that your solution group was non-trivial. So whenever H has an element of order 2, you have a non-trivial solution group, just because there are operator solutions to the linear system. So that was actually somehow the hard part. And now to find whether or not this kernel is trivial, that's just linear algebra. So you just try a bunch of groups, see which one works. And we found that for all n greater than or equal to 7, the alternating group, an, if you build the linear system like this, then you get that the kernel is trivial. And by what we said before, because the alternating group has elements of order 2, it follows that the solution group is going to be non-zero. And that gives you asymmetric graphs with quantum symmetry. And I should point out that we did computer searching gap, and this is actually A7 is the smallest group for which you can do this construction. So it's a bit larger than the group you get for the Mermet-Paris square. Okay, so just to recap what we did. Now we took this alternating group an for n greater than or equal to 7. From that we built a linear system where the solution group is non-trivial but the kernel is trivial. From that we built a colored graph where the quantum automorphism group is non-trivial and the automorphism group is trivial. And finally we decolored to get an uncolored graph with the same property. That's what we wanted. Yeah, so that concludes what I had to say about the construction. I just want to close with this open problem that I mentioned before. We still want to know if there's a graph with trivial automorphism group and transitive quantum automorphism group, or even a stronger question that Adam asked, I think at some point, is even ergodic action of the quantum automorphism group. And people before have come up and asked me, what do we need to change in the linear system to get this? But I think you really need a totally different construction for this, because in this linear system, we went via a colored graph to an uncolored graph. And this colored graph is always going to force that there's different orbits in the quantum automorphism group. And I don't think we know a way to do that without fixing the color. So you really need a completely different approach here to answer this question. Thank you for your attention.
Questions?
I have a somewhat vague question. So you talked about this decoloring procedure. So you didn't mention this, but okay, the particular one you presented also doesn't change the classical automorphism group, right? And it's just clear. But could one think of any kind of decoloring where you, I don't know, you change, for example, the quantum automorphism group, but the classical one stays the same, or the opposite?
I think you can always recover the classical automorphism group from the quantum automorphism group by taking the abelianization of the C-star algebra. So if that's preserved.
Right, but could you imagine that some procedure was, okay, so let's be more specific, that you change the classical one, but the quantum one? No, so that does make sense, right? So you change the quantum one, but the classical one does not increase.
In principle, that's possible. I don't think we have a concrete example, maybe, but...
I guess there's subdividing edges before. So
oh, yeah.
in the paper before with David, we subdivided edges and this adds relations to the quantum automorphism. So,
yeah, so whenever you have a result like this, then the end result looks, yes, okay, that looks like the normal thing to do, but actually there's hidden a few steps where we tried something that didn't work. So you have to be a bit more careful in this quantum case. Yeah.
Is there a way to decolor using cycles of different lines?
I'm not sure if you can even do that for classical automorphism groups, but yeah, it's not something we have looked into specifically. Maybe one thing I should mention is that our decoloring now, we can also decolor in such a way that not only the quantum automorphism group is preserved, but also this quantum isomorphism algebra between two graphs. So you can decolor all graphs in a uniform way so that the quantum isomorphism algebras stay isomorphic. So that's kind of nice.
So, you know, like which groups arise as solution groups? Like, do you have any idea? Like, I give you a nice finite group, you know?
So I have a construction of, this gives a construction of, for every finite group you take, you get some solution group over that group. And I think this is universal in the sense that it's somehow the smallest extension of H that's still a solution group. But I don't, it's something I'm thinking about, but I don't know easy criteria to see when are they equal, or is it always a central extension, or what happens there. So that's, especially in relation to the Frucht property, that's really interesting to try to find which groups are these actually, which solution groups do we get. We did find that for, if you start with A7, then the solution group is going to be the triple cover of A7, which is still a finite perfect group. And another one is if you start with the Mathieu group M12, then, or I think any of the Mathieu groups, I think the solution group is going to be itself. And also for the alternating groups, AN, where n greater than or equal to 8, I think my computations show that it's always equal to AN there. Somehow A7 has this sporadic triple cover that the other ones don't have. But I don't think I could prove that yet. So I would conjecture that maybe the alternating groups of AN, where n is at least 8, would work.
Did you try working over other fields as well?
Not really. I remember discussing this with David at some point, but I don't remember what the conclusion was. Yeah. So maybe one thing in the inhomogeneous case where you have two graphs, we don't even know, or I guess the first examples are now showing up of linear system games modulo odd primes, where you have a perfect quantum strategy but no perfect classical strategy. But this is somehow much harder to find than modulo 2. And also the techniques in our proofs are a bit simpler modulo 2, because they're, if you have a unitary of order 2, then it's just like self-adjoint, so it's a bit easier to work with. Yeah, I don't know if there's going to be obstacles or not.
Okay, so we have a break next, and then we'll have another talk in roughly half an hour. But first, let's thank our speaker again.